Hello everyone, I'm Andrius Mažeiva and today from Adform, and today I'm going to present my story how actually we transformed batch-based data processing pipeline with the power of Aerospike. So at first, in short, my story in Adform. I joined Adform 5 years ago as a technical product owner and data processing team with a goal to lead the refactoring of existing processing flow to support constant growth of data flows and data sizes, amounts, and to ensure better availability. A little bit about Adform. So Adform is integrated advertising platform built from the ground up as a one integrated platform. And the company is already for 17 years in the business, and it's a leading advertising technology company which provides software used by buyers and sellers for automated digital advertising. So we are providing the supply-side platform, buy-side platform, data management platform, third-party ad server, so full ad stack services. So let's take a look what actually ad serving in Adform is. It's a simplified view. So we have a user who visits some web page. Inside web page, we have so-called placements where banners should be shown. And these placements, we call them tags, are performing requests to our ad serving. So ad server makes a decision what banner actually to show and returns needed banner scripts to the web page. At the same time, logs the so-called impression information to the Kafka. So Kafka is a distributed log where all actually events which happens lands in Adform ecosystem. So what happens next? Scripts renders banner in a placement. So in this case, in this example, we see 3 banners are rendered. It doesn't matter actually, is it these banners happens because of so-called TPAS, where there's agreement between web page and the ad server, or it's before real-time auction happened. The actually ad serving schema is the same. So what to do with this data, which we finally have in Kafka? So each impression actually comes from some user, not always, but sometimes we manage to identify the user. And we call this we identify by some ID, we call it by cookie ID. And we have some goals from business, some questions to answer. So the questions are, for example, was impression unique? Was impression unique today? Was impression unique per campaign, etc.? So we need some historical information about each cookie ID to be able to answer these questions. And for sure, we have a question how actually to store and to access these cookie profiles. So let's take a look at the legacy processing data flow, how it looked when I joined Adform and the challenge I had. So we have a Kafka, where is all the initial information, the logs lands. Yeah? And we have some processing instances which are responsible for actually doing the stuff, so doing all the attribution. Inside each instance, we have a Microsoft SQL server, which was used as a main storage. And we have so-called the router, who is responsible of taking all the initial data from Kafka and to route it based on the cookie ID mod 100. So this means we are dividing all the traffic to 100 separate parts, which are not intersecting with each other, because we always determine to which instance to send. Yeah? Actually, all this router runs on the Storm in our case. So let's take a deeper look what actually happens in each processing instance. So as I mentioned, all data lands in raw input from router lands in raw input table. After that, we have a so-called pre-processing, which is responsible for forming input batches. For each batch, we have so-called, in our case, processing, which collects all individual cookies from the batch, loads all the profiles from the cookie profiles tables from Microsoft SQL Server. After that, processes all impressions based on profiles. This means looks at the history and attributes is impression unique or not, and for sure saves the new information to the profiles to be able to attribute the future impressions. Yeah? After this processing, we are doing 2 steps. We are saving all modified profiles back to SQL Server, and at the same time saving the processed batches. Everything happens in transaction. And the same thing happens in each individual processing instance. Okay, so a little bit how profiles were stored in Microsoft SQL Server. So definition of records, there are two types of records. So it's a cookie and a cookie profile. So cookie is a record defined by cookie ID to store general information about the cookie, like first seen time and last seen time. And the cookie profile by itself is a record defined by the same cookie ID plus so-called tracking setup ID, which is individual to each client to separate different clients' contexts. And in this record, we actually store the actual profile as a binary field. We use the protobuf, and we use first seen, last seen times, and other less important attributes. So if to talk about the structure of tables in SQL Server, so one table for cookies, and dynamic number of cookie profiles tables, where new table is created in case the amount of records in one table becomes too big. So it's dynamically sharding and avoiding too big tables. For sure, if we would store cookies forever, we would die. Yeah. So we have some custom expiration logic, not maybe custom, but just expiration logic, which is defined by two rules. In case we see new cookie, we store it for 7 days, because it's a huge possibility that we will never see it again, because all our, how to say, ability to determine user is probabilistic. So we don't know with whom we are dealing actually. So we're just trying to set cookies and to base everything on that. And if cookie is active for more than a day, so this means we have 2 impressions with bigger interval than 24 hours. This means it looks like we managed to set the cookie, and we will see this person later. So we store it for 30 days. If to talk about the process, so in the SQL Server, so once a day we run a huge job which scans all the tables, joins cookies with cookie profiles, because in cookie we have first seen and last seen day, and deletes all the records based on the rules I mentioned. So it's quite complicated and quite long process which had to be performed once a day. Okay, so what problems we had with this legacy flow? So first, Microsoft SQL Server performance and batch sizes. So one more time about the principles of batch processing was when we have a batch, we scan all the tables to find all the needed profiles, and we're actually deleting them from database, deleting in a transaction. Yeah? So next step, when we load everything with deletion, we do the processing, as I mentioned, attributing the impressions and putting new information to the profiles. And after that, we are putting modified profiles back to the tables and saving the batch. Everything happens in one transaction. We are committing transaction. If something bad happened, actually nothing bad happened, because everything is in transaction, and we can reprocess the batch without no problems. Scanning by itself is costly operation. So, and it depends not on the amount of how many records we want to find, but on the amount of how many records we actually have. So that's why batches had to be big. The batches was for half an hour's data. I don't recall exactly amount of records, about 50 million in one batch, something like that. So just to optimize to do less scans as possible. So big batches for sure results in a bigger statistics delay, because you have to hold all the data to wait until batch is formed. Later on, you are spending 20 minutes to process the batch. So everything results in actually bigger time than you can show the statistics for the users. And maintenance windows were needed to perform various Microsoft SQL maintenance tasks, like index rebuilds, even databases rebuilds, to keep the database running. And for sure, to run the jobs for expiration, I mean for deletion and not needed records. Another problem was scaling. So let's say initially we have 5 servers, and as I mentioned, we have all this routing based on cookie ID, so it's easy to distribute all the mods to the 5 servers. But let's say load is growing, number of impressions is growing, sizes of profiles are growing, and we need to scale. And let's say we are trying to add 2 new servers. So what actually happens? So at first, somehow we need to reshuffle the data. So we have to take data from local instances and to move them to new ones. And it's not only about profiles. We have to reshuffle the data which is in the fly. So this means something which is already inserted, even in the batches, but not processed yet. And it's quite long operations to do. Another problem is it's not so easy to distribute the load equally, because in this case, if you add 2 additional servers, 100 is not divided by 7. So this means some server will taking more load. And let's imagine if you want to scale every week or every month, so it's quite costly and well, operations which devs don't like usually. And one more problem with such approach was availability and single point of failure. So what would happen if one instance goes down? At first, everything stops. Stops because the router by itself is not managing to push some of the data, some of the cookie mods to the destination. This means consuming from Kafka stops because we can't commit offsets. So we have to wait until server is restored. Everything is okay if it's just temporary problems. Just we had to restart the server, just electricity was gone and it's back. But if we have some serious problems with server and we can't restore, or maybe even disks are broken and we can't put them to another server, we can, in the worst case scenario, we can lose the data. Good thing is this never happened, but it was a risk. Okay, so solution. Instead of using local storage for each instance, we decided let's try to use Aerospike cluster for storing cookie profiles. So to move cookies and cookie profiles from local storage to external cluster of Aerospike. Good news was that actually minimal changes was needed to the solution to implement that, because if to look how a solution looked like and how it changes when we're adding Aerospike cluster, so actually we're just changing the storage and the same batching processing remains. Just instead of looking into the individual storage, we're looking outside into the cluster. This was the initial idea. So why Aerospike? So Adform already had some experience in Aerospike usage, and we had only good impressions about it. And Aerospike feature set meet our needs for the profile storage. So it has really fast access for the data by record key. It was dealing with profile expiration out of a box with TTL, time to live functionality. It has needed scalability and availability features. And the main benefits we saw with this approach was possibility to change the storage without big refactoring of really complex overall flow. And changing approach from scanning to lookup by key should allow us to reduce batch sizes. At that moment, we didn't know how much and how the system would behave, but we had at least such expectation. And the scaling of storage and processing instances after moving the storage out becomes an independent process. Because if we need more CPU for processing, we can scale processing instances. If we need to scale the storage itself, it's scaled, separately. And no loss of profiles data in case we have one server's outage. So these are main benefits we saw while designing the solution. So how the initial design looked like. So we designed the Aerospike cluster of 4 nodes, each with 7 terabytes of SSD disks, 756 gigabytes of RAM, and the Aerospike version at that moment was 3.5.15. As I remember, this was the newest version at that moment. We designed it as one namespace with replication factor 2 and with 2 sets, one for cookie profiles. The key is defined as cookie ID plus ID of tracking setup. Individual profile for each client, very similar as we had in the SQL server. And profiles data is stored in a binary type bin, plus additional less important bins. So second set was for cookies. The key is defined as a cookie ID for storing cookies first seen and last seen time, which are still important for us for setting needed to tell for the cookies. And we had to store the reference to all existing cookie profiles. Initially, we tried to use the secondary index, but decided to stick to the own custom implementation and approach. So actually, we are managing the secondary index inside the profile, just to have all references to the cookie profiles to be able to extend their details. And decision was made to introduce additional REST API layer between the processing instances and Aerospike to isolate the processing solution from actual storage we're using, and to isolate from this custom logic we have to have for maintaining this references, time to lives, and other stuff. Okay, so how redesigned processing data flow looked like in the solution. So we have everything the same. Have a mouse. We introduced the API layer, as I mentioned. And yeah, loading, doing the stuff, saving it back. Yeah? One problem we have with this approach, we lost a transaction. So this means we no longer have a possibility to reprocess the batch without no impact on the data. Yeah? To solve that, what we actually did, we decided, okay, let it be. Aerospike is flexible enough, so let's store the last processed transactions in the profile to be able to reprocess. So when we load the profiles, at first we are checking maybe this exact transaction, which has own individual ID, was already processed. If it was, we're taking all the processing result from the history and not doing processing at all. And for sure, deleting the historical log of the processed transactions, not to grow up the size of profiles too much. Yep. So for sure, we had somehow to migrate the data. So we created a plan, and the plan was just let's add additional step in the processing pipeline before starting actually doing the processing. Let's read all the data from SQL Server. Let's push it to the Aerospike via API, and after that, let's do a standard processing. Yeah? This, for sure, this happens in a transaction. So if we manage to push everything to Aerospike, we are deleting the transaction. If not, it's not bad because we can repeat and just overwrite the records. Nothing bad happens. And after the migration of individual portion, we actually are doing the processing already by loading data from Aerospike. So migration. Migration started. Everything went very well. Data in Aerospike started to grow. Aerospike servers, Microsoft SQL server sizes started to reduce. Even performance was okay because as soon as the Microsoft server table started to reduce, the scans become faster and faster. All migration was intended to finish in 30 days because, as I mentioned, we have been storing the profiles for maximum 30 days. If they are not touched via 13 days, we're just deleting them. After 2 weeks, suddenly everything stopped. And it was a huge surprise for us. And Aerospike just stopped accepting new records. After 2 hours investigation, everything is stopped, so it's production. So it was quite challenging situation. We found out that we reached a limit of 256 gigabytes of maximum RAM, which can be used for primary index. It was a limitation which at that time Aerospike had. Later on, it was removed. And for sure, we haven't tested such amounts in dev environments. It was a mistake, and we haven't consulted Aerospike about our cluster setup. Main question was, so what to do? Because we are stuck. We can't move back. We can't move forward. And we are in production. So we have to do something. Time is ticking. Kafka can store the data maximum for 24 hours. Later on, data is just gone. So good thing is, but actually, we are running on premises, and we had opportunity to find internally other servers. So we find additional servers and started adding them to the existing cluster. And as soon as the first server was added, everything went smoothly. We catched up the time. Data delays disappeared. And we just kept adding the nodes until everything was migrated. And we ended with 12 nodes in a cluster after the migration. And for sure, the utilization of servers was really, really low, because as I mentioned, we had a lot of RAM, quite a lot of SSD disks, and we have been utilizing maybe 5% of each server as a result. So what's next? What to do with this situation? So we decided to enable efficient hardware utilization to add some sharding to the Aerospike. Instead of using one namespace, to use 4 namespaces in one Aerospike to avoid the limitation of one namespace size. And this was made in our already used approach with modding the cookie ID. So we just modded it by 4. And as far as we had the API layer, it was really easy to adjust what in case you just have a cookie, mod it, and determine to which namespace to save it. So what we did, we changed the solution. It was really a fast change, as I remember. We created additional Aerospike cluster. Once again, with initial setup with 4 nodes, 7 terabytes of SSD disks, 756 gigabytes of RAM, the same version, and modified REST API layer, which was performing data sharding. We adjusted existing migration logic, which was reading from Microsoft SQL Server, to read from one Aerospike, to load it, to push to new one, and delete all data. And started the migration again. So after one additional month of migration, we ended in a solution which was running on initially planned hardware with a small adjustment what we had sharding inside, and everything was intended and working perfectly. So impact on performance of Exchange, after migration was finished, we changed the batch sizing to 30 seconds instead of 30 minutes, and everything worked great. Later on, maybe we increased the batch sizing to 1 minute, but because of different reasons. Removal of huge cookies and cookie profiles tables from local database had significant impact on Microsoft SQL Server performance, because Microsoft SQL Server was still used, but for different tasks, not for storing the profiles, but for storing all the batches and raw input tables. And individual performance of a processing instance increased about 3-4 times. And not only the time decreased, but actually we gained much more performance with the same instances. So main lesson learned. Consult Aerospike support while planning your new Aerospike-based solutions for correct cluster sizing. Otherwise, you can face very unpleasant situations in production, because such things can be sadly tested in dev environments. OK, so now let's go back to the ad serving, how it works. So one more time, user visits web page. We have placements. Placements are rendering the banners. Ad server is logging the impressions. And actually, serving is not ending at that time. We keep tracking what actually happens in the page. So our scripts are continuously measuring is banner in screen and trying to determine for how long during the next 10 minutes after banner was served actually it was in screen. We call it visible by a user. And this measurement continuously sends the events to the same ad serving with viewability information, and we are getting up to 5 requests for each individual banner about the viewability. At the same time, user usually, at least we expect, are interacting with banners. So if it's a video banner, we press play, stop. If it's some rich media banner, we can play some games even on banners. So banners are sending different events also to the same ad server. So we're getting more information to the same Kafka. And as a result, we need some additional impression enrichment. In this case, we need to answer a question. So was impression viewable during next 10 minutes and for how long? And did an engaging event happen during the same next 10 minutes after impression was served? So in this case, it's not about looking at the history. It's looking at the future. And we need somehow to join the different streams with 10 minutes window and to apply some custom logic. So let's take a look how actually it was implemented. So it's a more detailed view of totally the same processing. So we have totally the same routing. Just in this case, we're routing not only impressions, we're also routing the viewability information and the events based on the same cookie ID mod. And it lands to the same Microsoft SQL Server, just a little bit different tables. I should have more detailed view. Nope. So impressions lands in raw input table, viewability in raw viewability table, events in raw events table. And in the preprocessing step, which is responsible for forming the batches, actually for each impression, we are joining with raw viewability information. So we're doing to look up after waiting for 10 minutes, what was it viewable and for how long. And also looking if any engaging event existed during next 10 minutes. And forming a batch. At the same time, events also added to a batch, because events also processed in the same way as impressions and are needed for statistical information. All the remaining part already with Aerospike cluster in place remains the same. So what problems we have with such joining on SQL side? So at first, joining for the viewability is quite a complex one, because we have many viewability events, and we need to find the lastest one. So the query, SQL query, is quite inefficient. At least we would like it to be more efficient. And the events table also is used for two purposes. One is to look if there was an engaging event, so look to the future, and at the same time to push them to the processing batches also. And we need for sure separate processes for deleting data which is already not needed. And if you know SQL Server, so if you do something with the same table, not just a simple operations, but huge addings, joinings, deletions, it conflicts the processes between each other. And we have constant locks, even deadlocks, and this process just can't happen at the same time. And also constant adding and deleting data in the tables makes native SQL indexes, well, very inefficient, because you constantly have to rebuild them to at least to gain some performance. So, and if tables are growing, everything slows down. It's really hard to ensure the stability of a process. In the picture I showed before, it was only one Kafka cluster shown, but actually we have 5 Kafka clusters all across the world. So to take data from everywhere, if you have some network problems, something is delayed, we can get some data and the tables are growing, but we're still waiting for remaining ones. So it was really, really hard to control all the process. As the bigger tables are, the slower everything works. So we thought about possible solution and defined ourselves a goal. So let's try, instead of joining data inside an individual processing instance, to join the streams before routing. So as far as the joining window is quite big, it's 10 minutes, we need some temporary storage to store viewability and events information. And in-memory Aerospike cluster perfectly fits here. We wanted to have a separate process for writing events and viewability to Aerospike. And we wanted to adjust the current routing process to do a lookup for each individual impression before pushing them, routing them to the individual processing instances. So how redesigned the processing data flow looked like. So as I mentioned, we introduced a new process on the same store, which was reading all the events and viewability information from the Kafka and pushing them via API to the Aerospike cluster. Another job, the router, it has artificial delay for 10 minutes. This means don't take information, hold it until 10 minutes passed, and also sync with another process. Do a lookup. This means enrich the impression with viewability and event information, and push them to the processing instances. So processing instance was totally the same as it was, just some parts of the joining was removed. Everything remained the same. So it was incremental change of the process. So what was the design of a solution for stream joining? So it was 4 nodes of Aerospike cluster with 512 gigabytes of RAM. It was in-memory Aerospike storage, totally no SSDs and even no disks for storing. It was in-memory namespace with replication factor 2, and it was a flexible API layer which enables to define new sets for separate use cases. It supports different update strategies on records and bins level, like always update, keep last by date, creative not exists. Because if to talk about examples for viewability, we needed keep last by date. Because when we process data from Kafka, it can come in any order. So you are not controlling which event you would get first. So we are updating only if we are taking the new event. For the same events for engaging, we used creative not exists because we need just to know if any engaging event happened. And the API had the ability to enable to define a custom total for each set. Good thing was that there was no limitation on record size because data was kept in memory. So we designed a solution which potentially could be used for any joins, whatever size of data we want to join. So potential problems we had with such solution was how actually to know if it's okay to do a lookup from a router. This means are all viewability and events information already in Aerospike, because we are 2 totally separate processes. And what if memory Aerospike will lose more than 2 nodes at the same time? Because how to actually avoid the possible data losses? Because the servers are just in memory servers, just electricity can be lost, whatever can happen. So we decided we need to have something to have a synchronization between processes. We introduced a separate independent process. We are calling it data delays collector, which is continuously checking the committed Kafka offsets, extracts the actual time of a transaction which this offset is actually representing, and push the calculated time to the same Aerospike via API. Why same Aerospike? Because as a result, yes, we have a possibility always to check from whatever process how other processes are dealing and with what time they are actually dealing. And at the same time, as the data is pushed to the same Aerospike, in case we lose more than one server, we actually lose and the data delays. And this allows us suddenly to stop everything until data is restored. It was OK for us to lose the data because we can simply roll back the offsets, replay the stream, and get all the data back. So that's why we don't need any persistence. And actually, it was only one time when actually we had an outage in data center when electricity was lost, and we had to repopulate the data. So it was really, really real, rare conditions when actually such things can happen. Yep. So what's next? Stream joining solution, the same I mentioned, together with the data delay collector, is already used for 5 different use cases, and including one which is for sessions calculation. The join window is even 6 hours, and the data by itself can contain megabytes of information. And the same data delays API currently is used as a main source of stream processing health monitoring, because we have the ability to see not only from technical perspective how processes are dealing, but actually how much time they are delaying from the data we have in Kafka. And these services are on this, and this synchronization ability to synchronize between processes allowed us actually to make our solutions less complex, just to have smaller services for processing and just to synchronize them in time. So conclusion, adding Aerospike to processing flow allowed us to speed up all the flow. So if to look what we had before, so average delay for data processing reduced from 4 hours to 15 minutes. And these 15 minutes actually including the 10 minutes delay which we have, which is required by business for waiting for viewability and events information. And Aerospike enabled us to scale on the most critical paths. By utilizing Aerospike, overall costs of a solution reduced both from hardware and both from operational perspective. And yeah, Aerospike is just great. Thanks and questions. Okay, this router actually is a Storm application. If Storm is, well, maybe you know Flink, yeah. So it's similar as a Storm, just a little bit maybe older. Yeah? So it's a real-time stream processing platform which enables to consume the stream and to do whatever you want with that. Yeah? So yes, it's a custom-made process which consumes the data, does even more things, and yes, it's, well, on application level, has all connections to the different SQL servers and just inserts data to the table.
So it's on application?
Yes, it's on application level. It's, well, I'm showing the simplified schema. Actually, we are attributing more than 100 different fields in the processing, and we are doing a lot of enrichments with metadata and other stuff, which is also happening in the in this case, in this router and the bridge, and in pre-processing, in processing, and so on.
How many instances do you have
for Storm? Currently, it runs. We are running Storm on Mesos, and Mesos contains 40 physical nodes. But it's used not only for that; it's used for 50 different topologies
They
are running.
contain statements, right?
Yes and no. Storm is using Zookeeper for storing state.
So like if we're zooming into that small piece.
Yeah, but I wouldn't need not half an hour. I would need all of a day to zoom everything.
That's interesting. Thank you. More questions?
The question I have is, how did you think of doing this? Typically for batch processing, people don't consider Aerospike at all. So how did you come to this in your thought process that you could, because you really improved it from hours to minutes. I've heard this anecdotally from some customers that your customers were pretty good because you explained. I'm just curious as to how you even started thinking that you could do this.
Okay, so at first, why we're using batch processing at all? Yeah, so the main problem is that somehow we need to order the data. That's why we need some kind of relational stuff where we push the data, wait until everything is in place. We need to order it and process everything in time how it happened. So that's why we need some kind of relational stuff between. And yes, as I mentioned when I joined, we really had the problems that it was constantly delaying. And the main problem was the speed, how fast we managed to get the profiles and store them back. And we need to find some different ways how to do that. And we didn't have a lot of time, actually, because in our business, the load is constantly growing. And it's always a question about survival. Will you survive the next high load season? So we had quite a limited time, and we had to solve it. So, and as I mentioned, we already had a really good experience about Aerospike, about its ability to, because it was actually key value task. So you have something which you know the key, and you need to get it, and you need to get it fast. So that's why it was Aerospike. And it was, we managed to implement that maybe in 2 months. I can't recall exactly, but it was really fast implementation. And it allowed us to do the change without a huge refactoring of all the process. We just didn't have time for that. And yes, it's not a standard case for Aerospike usage. So this is, because we have the same bidder which uses Aerospike and other stuff in our ecosystem, but this is a little bit different case, which I wanted to talk today. And the same joining solution, also, there are many different solutions, but as far as we had a really good experience with Aerospike, so we decided why not? Why to use other technologies? Why not to stick to the same one? Because it's easier to maintain for the developers to learn and to use. That's why we decided to use in-memory Aerospike for the joining.
Thank you.
Good.